Thank you very much for the introduction and also for the opportunity of being here, for setting up these nice conferences or symposium. I am very, very happy to be here. I really love this city, and when I saw that there was this minisymposium going on, I said I want to go. And also from the experience from last year, it was very, very interesting to meet virtually, but meet many people working with mathematics and arts, as we are doing. This is John Ward with Jaime Lobato. He's my friend and colleague. He's coming from the arts part. He's a composer. He studied music composition. And I am coming from the academic part, from the, I am a mathematician. I am been following this academic path a little bit more. This is for,
that should be,
yeah. So a little bit of, so a little bit more of this background. So as I said, I am a mathematician, and I came into the world of the generative art because of my thesis on all the things that I studied was aperiodic tilings. And while I was writing my thesis, I realized that I had to draw that many aperiodic tilings that I learned to code them actually. And this naturally took me to this community. And that's where I met Jaime. Jaime was a musician, and he was already working with this software super collider, which is like a computation and synthesizer, super complete. You can do so many things. And we started this collaboration that, well, it was mainly me with this group of generative artists and live coders. And from this collaboration, we started this project, which is called the Laboratory for Visualization and Sonification of Mathematics in the Institute of Mathematics in Mexico's National University. And this is not a research project. It is an outreach project mainly, and like an art project also at the same time. So a little bit of background. This is, if you do watch the video on YouTube, then you will see this part repeated, because there is just a recall on what are the kind of things that we started thinking with this project. And there is this book by Diderot, which is called the Letter on the Blind for Those Who Can See, which is like it's an essay where he draws some questions regarding the understanding of mathematics and the visual understanding of mathematics. And he talks about this character, Sanderson, Nicholas Sanderson, which was a blind mathematician who created and developed a method for teaching and learning mathematics for blind people. And there he poses some questions that really make you think about how much of our understanding is constrained, or it's dependent on our visual understanding. And it's related to the Molyneux problem, which is like a philosophical problem, but it really was one of our first discussions in this project. And also these other two books are also very important for cement, I don't know, the pillars of this project, because as I am coming from an academic background, there has to be some academic start where I should start from. And there are these two books which are talk about the origins of sonification and the basics of sonification. And it's already a theory that's been developing from the past couple decades, and it's attracting different kind of scientists from different disciplines. No? So these books are more or less a culmination of this start in 1992, 30 years ago. It was founded the international community for auditory display, where all these ideas started they started gathering all these ideas, and they started this research in auditory display, in this theory of sonification. And its goal at the beginning was only to transmit information or data through sound, and this could be as broad as you think, as you want. So in the last few years, this sonification got into the mainstream science media, as this article was published in Science, and they made the sonification of the DNA chain of the DNA. It was actually very simple what they did, but I was kind of surprised that it came up to this page, and you can find this both the article and the sound. It's 2 hours of sound, if you want to go there. But I like that it is there. In the end, this other sonification, you can find it in NASA's website. Just listen to it. This you get to find it in NASA's website, and as I mentioned at the beginning, this project is an outreach project, and when you think about outreach of science, then like the big things are planets and dinosaurs and stuff like that, and mathematics outreach is just too tiny compared to them. So but in this sense, like it's like maybe we are getting a step further if we try to do outreach with sound. Okay, so also last year I showed some of our first examples. This is one of them. I'm not going to play it complete because you can watch it in the YouTube. But this is a sonification of the procedure of the algorithm for solving the Hanoi towers. And what we are doing here is that we assign an octave for each disk, and we assign nodes to each of the 3 sticks. So we want to move disks among 3 sticks, and this a movement. Well, you listen. So there are 2 sounds, which is the origin and end of the disc that you're moving. Huh? And another example that we also showed last year is the like symmetries of Frieze patterns. I'm not going to play them because you can actually see them very clearly. But as most of we know, there are only seven groups of symmetry for Frieze patterns, and these are these seven groups. And you actually can distinguish the asymmetries with the sound. It's easy to do that. You don't have to have a very educated ear to distinguih, to realize or to find these symmetries in the sound. This is also a third example that we showed last year, which is sonification of fractal curves, which we started with. But it is actually, well, I'm going to play a couple of them. So we start with this iteration. It's only 3 notes. It's a triangle. It's only 3 notes. We take 3 equally spaced notes in the 12th scale, in the 12th note scale, and it sounds like this. the sounds are following. Just if you play it at once with the Logos programming language, this turtle that you would follow some instructions, then this is exactly what we are listening to. And so on, no? and this is where we started like playing in different paths, following different paths, because this in some sense can be used just for playing music, for generating music, which is what my colleague Jaime did with this one. This is basically the fourth iteration of what I didn't play. This is the fourth iteration, but now like synthesized and also specialized and more musically produced. There are 4 iterations sounding at a time. 2 are going in one direction, and the other 2 are going in the other direction. Each of them is a different instrument, and this is like a different path that Jaime was following. But the other path is to start trying to differentiate different L systems. L systems, there's a short for Lindenmayer systems, which are like symbolic systems that you would iterate, and you would have start with a symbolic, with a symbol, with a letter A, for example, and you give a rule in which you start iterating and generating bigger strings. And the previous sound that I showed, this one, it's built with an L system, and these are also L systems. So here, one thing that, well, I'm going to play one at the beginning. Start with, oh. Yeah. But here I want to stop a little bit here with the L systems, because this is the first one we listened to, and so let me play another one, a different one, but also a fractal curve, but a different one. And let me play a bit more of these other ones, because I claim that here what I wanted to point out is that I believe, or I think that we can listen, we can differentiate these two kind of objects that we've been playing their sound, the two fractal curves that are closed curves, and these three that we listened together in the more L systems button. I don't know, I cannot put it in words, but I feel that when they branch, they sound together as when they are closed curves. There is one bachelor student which is doing his thesis about that, and this is the main question that I've been asking him. What's the big difference between how can you actually tell, or what's the rule to differentiate these two essentially different kind of L systems? So I'm going to go back to the presentation, which I don't see there. That's and one other example that we've been exploring, it's of course symmetries. Symmetries, as I mentioned already, we played with them with the freeze patterns, but there was another, I believe that there are, in music, there are way more symmetries than just the symmetries that we could actually draw in a music score. So we started playing with this group. This group is the group of symmetries of the dodecagon, 12 again because of the chromatic scale with 12 notes. And so we took all the symmetries of the possible symmetries, which is rotating this thing and reflecting it, and we do know a lot about these groups of symmetries, and these can be written as just swaps between the vertices, so there's like the permutations. Basically, you can think about symmetries of these as permutations of elements from 1 to 12. So this is not going to sound that very nice, but I want you to try to listen a little bit. I'm going to play the 12-note scale, and then I'm going to play the permutations, the group elements of the acting on the scale, and it's okay. Yes, the sound is boring, but the question is, can we actually identify some properties from the group elements by listening to them? And the answer is yes, these two, at least, order and sign. You can tell the order and the sign if you count the length of the steps that you are breaking your scale into. If you listen closely, there were all the scale, the stair or the steps would be broken into two, and if you count how many where the up and then the down came, then you would be able to tell the order and the sign. This is maybe a little bit too much for an outreach audience, but still it's what we are looking after. We are trying to identify mathematical properties through sound. No, so it's in some sense it's one of the goals of this project. And now that we were already playing with this group and making it act in an octave, then I'm putting this example here because basically I came to this thing, and my colleague Jaime told me, well, what you are doing here, it's something called the 12-tone technique, which is a technique for composing atonal music by Schoenberg. And atonal music is something that it is not tonal music, as Professor Hempel was explaining early in his talk. There is this resolution when you listen to some sounds. There is this resolution of chords, and this is all tonal music, and that's how most of the music it's composed. But then this sir started composing music which says, like, let's avoid the tonality. Let's avoid tonality. And he created a rule for creating this kind of atonal music. And while playing with this group acting in an octave, then we were actually playing with this 12-tone technique. And so a dodecaphonic series would sound like this. This is, I think it's 4 compasses playing 12 different notes each compass with different times, just ensuring that there would not be repetitions of a single note in a single time. So a little bit to like try to sum up some of these ideas, summarize these ideas. What we are looking for is to identify or try to identify some mathematical properties through sound. And so far, we have explored at least these 3: symmetry, recursion, like in the Hanoi Towers. It's one example of a recursive algorithm that you get to listen if you listen carefully. Autosimilarity, it's like this these fractal curves, and that are played on top of if you are playing the 3rd or 4th iteration of these fractals, then you would play all 4 iterations at a time, and so you get to actually listen to the autosimilarity, how the fractal is built. And some people say that you should not talk about what you don't have, but it's not that we don't have, it's just that we don't have conclusions about it. And it's that we are now exploring multidimensionality through sound. And this is, I'm going to play 2 sonifications more. How am I with time?
We should come to.
Okay. Well, I just want to maybe briefly mention that there is in this book, there are some good some ideas about why aural perception it's good for exploring things, because in some sense could be finer than visual perception. For example, if there are 2 waves of light, one yellow and one red, and they are crossing, then you would not see yellow and red, but you will see orange. When it's about listening to, you do get to listen 2 different waves. So it's something like that. He says many things, but I am just briefly summarizing what he claims. And I'm just very quickly going to play these 2 different sonifications, which is, as I mentioned at the beginning, I started with the generative art thing through tilings. And tilings, these kind of tilings, there are 2 different ways that at least 2 different ways that you can construct them. One is with this iterative process, similar to the L systems that I already talked about. And there is another way that it is basically projecting pieces or stripes of a 4-dimensional space. So this multidimensionality We started exploring to this. Still, we cannot tell anything about the fourth dimension through the sound, but it's already in our discussions, and we have two different approaches. The first one is mine as a mathematician, and the second one is Jaime's as a composer. What we are listening to here is actually this image. Well, this is the image. There are 4 iterations. Each iteration is an instrument. So the first iteration is only in the corners. And then this is the fourth iteration. The blue one is the second one, and the red one is the third one. Okay. Well, you can listen to the rest of the sounds in this web page. There are all the sounds there, and you can also find our content. From the presentation.
So